Gravity feels obvious. You feel it every time your feet touch the ground. You feel it when you drop an object and watch it fall. You feel it when you stand up too quickly and your body reminds you that something is pulling you downward. Because it is always present, because it never turns off, gravity feels simple. It feels like something we understand instinctively, something that does not need explanation. Things fall. Heavy objects feel heavier than light ones. The ground is down. The sky is up. Gravity feels like common sense. But common sense is not how physics works. Physics begins at the moment intuition fails. And gravity is one of the earliest places where that failure becomes unavoidable. When you say that an object falls because of gravity, you have not explained anything. You have only given a name to what happens. You have described the effect, not the cause. Saying that gravity makes things fall is no different than saying fire burns because of fire. It feels explanatory, but it adds no new understanding. It only replaces the mystery with a familiar word. Modern physics does not begin with falling objects. It begins with measurement. When physicists say they are measuring gravity, they are not measuring heaviness. They are not measuring downwardness. They are measuring how objects accelerate relative to one another, how clocks tick at different rates, how paths curve in ways that cannot be explained by motion alone. Gravity, as physics encounters it, is not an experience. It is a pattern hidden inside numbers. Consider something simple. You release two objects at the same time. One is heavy, one is light. They fall together and hit the ground at the same moment. This already contradicts intuition. Common sense suggests the heavier object should fall faster. That idea feels so natural that it dominated human thought for thousands of years, and yet careful measurement shows it is wrong. Mass does not control how fast something falls. Something deeper is at work. What physicists actually measure is acceleration, not speed, but the change of speed over time. Near the surface of Earth, objects accelerate downward at a steady rate. That rate can be measured with astonishing precision. It is not approximate. It is not vague. It is a specific numerical value that appears again and again in experiments, independent of the object being tested. This is already strange. Gravity does not care what something is made of. It does not care about shape, composition, or internal structure. A feather and a hammer fall together when air resistance is removed. Gravity treats them identically. Whatever gravity is, it does not behave like a force in the everyday sense of pushing or pulling different things differently. And then there is another problem, one that hides in plain sight. When you are standing still on the ground, you feel gravity as weight. But when you are falling freely, you feel nothing at all. Astronauts orbiting Earth are not outside gravity. Earth is still pulling on them strongly, and yet they feel weightless. Their bodies float, objects drift, liquids form spheres. Gravity is present, but the sensation is gone. This tells us something crucial. Weight is not gravity itself. Weight is a reaction. It is what happens when gravity is prevented from acting freely. The ground pushes up on you. Your body resists acceleration. That resistance is what you feel. Gravity alone produces no sensation. So already, intuition is misleading. The thing we think we feel directly is not the thing physics is describing. As measurements became more precise, the problem deepened. Clocks placed at different heights tick at different rates. Time itself behaves differently depending on gravitational conditions. This is not metaphor, this is measured fact. Atomic clocks separated by small vertical distances show detectable differences in time flow. Gravity affects time. Now gravity is no longer about falling objects at all. It is about how time unfolds. And yet even this is not the full story. When physicists map the motion of planets, they find that gravity shapes entire trajectories across space. Orbits are not the result of objects being pulled straight inward. They are the result of paths that curve smoothly, continuously, as if the geometry of space itself were guiding motion. What we call gravity appears not as a single effect, but as a consistent pattern linking acceleration, time, and motion across vast scales. From apples falling to planets orbiting to clocks ticking, the same structure appears again and again. And still, there is no simple picture. There is no tiny rope pulling objects together. There is no invisible hand dragging matter downward. There is only a set of relationships that can be measured, predicted, and tested with extraordinary accuracy, and yet remain deeply counterintuitive. This is why gravity has resisted explanation for so long. Not because it is weak, but because it is subtle. Not because it is rare, but because it is everywhere. Its constant presence disguises its strangeness. To understand gravity, physics had to abandon the idea that reality must match human intuition. It had to trust instruments over instinct, numbers over narrative, measurement over metaphor. And once that shift was made, gravity stopped looking simple. It stopped looking familiar. It revealed itself as something far more fundamental and far more mysterious than the sensation of falling. It became a physical problem, a problem that would reshape how we understand motion, space, time, and eventually the structure of the universe itself. Gravity only becomes clearer when intuition is stripped away completely. Once physics commits to measurement alone, the familiar language of pulling and falling quietly collapses. What remains is a set of relationships that refuse to behave like ordinary causes. Gravity does not announce itself directly. It reveals itself through consequences that are measurable, but not easily visualized. One of the earliest clues came from motion itself. If gravity were a conventional force, like a push or a pull, then objects experiencing it should behave differently depending on their internal properties. A stronger force should produce a different response in different materials. And yet, every experiment said otherwise. Objects of different mass accelerate in exactly the same way when gravity is the only influence acting on them. This was not assumed. It was tested repeatedly. Dropped objects, pendulums, carefully timed descents. The result never changed. This equality is strange. In everyday life, forces behave differently. Push a heavy object and it resists more than a light one. Pull a loaded cart and it accelerates more slowly than an empty one. But gravity ignores this logic. It treats all mass the same. The resistance of an object to motion, what physicists call inertia, increases with mass. But the gravitational influence on that object increases in precisely the same proportion. The two effects cancel perfectly. This coincidence is not approximate. It is exact to every precision we can measure. And it has no obvious explanation within ordinary ideas of force. As experiments improved, physicists began to notice something even more unsettling. Motion under gravity looks exactly like motion in the absence of gravity if the observer is falling along with the object. A freely falling observer cannot detect gravity locally. There is no experiment that distinguishes free fall in a gravitational field from floating freely in empty space. This is not philosophy. It is a physical statement that can be tested. Inside a closed laboratory, no local measurement can tell you whether you are drifting far from all massive objects or falling toward a planet. The behavior of objects inside the laboratory is identical. Gravity, then, does not act like a force in the usual sense. Forces can be felt. Forces can be detected locally. Gravity vanishes the moment you move with it. This realization quietly rewrites the problem. Instead of asking why objects are pulled downward, physics must ask why objects move the way they do when nothing appears to act on them at all. Freefall becomes the natural state. Weight becomes the anomaly. And then time enters the picture again. When physicists compare clocks at different heights, they find that clocks closer to massive objects tick more slowly. This difference is not caused by motion. The clocks can be stationary relative to one another. It is gravity itself that alters the passage of time. The deeper the gravitational influence, the slower time flows. This is not a small effect confined to extreme environments. It matters even on Earth. The difference is tiny, but measurable. Without correcting for gravitational time differences, modern navigation systems would fail. Position calculations would drift. Errors would accumulate. The technology would simply not work. So gravity influences time. It influences motion. It influences trajectories across space. And yet it cannot be detected locally in free fall. This combination is deeply unsettling if gravity is treated as an ordinary force. The more carefully gravity is measured, the less it resembles anything in everyday experience. Physicists began to suspect that the problem was not gravity itself, but the framework used to describe it. Perhaps gravity is not something acting within space and time. Perhaps it is something acting on space and time. This idea does not come from imagination. It comes from necessity. When a theory consistently predicts results that look geometric rather than mechanical, physics must follow the evidence. Orbits look like curves that objects naturally follow. Free fall looks like straight motion distorted by perspective. Time behaves as if it is stretched and compressed by the presence of mass. None of this requires speculation. It emerges directly from measurement. And so gravity begins to shift categories. It stops behaving like a force transmitted through space. It begins to look like a property of the stage itself, something that shapes the paths objects take, rather than pushing them along those paths. This is where intuition fails completely. Human experience evolved in a world where space feels rigid and time feels absolute. But gravity quietly undermines both assumptions. It suggests that space can curve and time can flow unevenly, and that motion responds to these changes automatically. The problem of gravity is no longer about why things fall. It is about why the universe has the structure it does, why motion follows certain paths, why time behaves differently in different places, why free motion and accelerated motion can become indistinguishable. At this point, gravity is no longer a single phenomenon. It is a thread woven through the fabric of physical law, and understanding it will require abandoning not only intuition, but the very idea that space and time are passive backgrounds. The story of gravity is just beginning. Once gravity is framed this way, as something that reshapes motion without announcing itself as a force, a deeper tension appears. Physics relies on reference frames. Every measurement depends on who is observing and how they are moving. Normally, changing perspective changes numbers, but not laws. The rules remain the same, even as descriptions shift. Gravity challenges this stability. An observer standing on the ground feels weight. An observer in free fall feels nothing. Both are legitimate physical states. Both can be described precisely. Yet their experiences disagree completely. One experiences a constant force. The other experiences none at all. And still, the underlying physics must remain consistent. This contradiction cannot be resolved by appealing to sensation. Physics does not privilege feeling. It privileges invariance. The laws must hold regardless of the observer. If gravity disappears for one observer, and Rye dominates for another, then gravity cannot be an ordinary force acting universally. Something deeper must reconcile these viewpoints. This is where acceleration becomes central. An observer standing on the ground is not motionless in the physical sense. They are accelerating upward, constantly. The ground prevents them from following the natural motion that gravity dictates. The force they feel is not gravity acting on them, but the resistance of the ground pushing them away from free motion. A freely falling observer, by contrast, is not accelerating at all. They are following the natural path dictated by gravity. In that sense, free fall is not forced motion. It is inertial motion. It is what objects do when nothing interferes. This reversal is profound. It means that gravity defines what it means to move freely. Motion that feels forced is actually constrained motion. Motion that feels effortless is what gravity prefers. Now imagine extending this idea beyond falling objects. Imagine applying it to planets, to stars. to entire galaxies. Objects move not because they are pulled, but because they are following paths that are already shaped. Paths defined by the presence of mass and energy. The question then changes again. What shapes those paths? Measurements show that mass alters distances and durations. Rulers placed near massive objects do not measure the same separations as rulers far away. Clocks do not agree. The geometry itself responds. Space is no longer a fixed stage. Time is no longer a universal flow. Gravity appears as a manifestation of geometry. This does not mean space bends like a rubber sheet. That image is tempting but misleading. There is no external direction into which space bends. The curvature is internal. It reveals itself only through relationships, through angles that do not add up, through paths that converge or diverge unexpectedly, through clocks that drift apart in their ticking. These effects are subtle near Earth. They become dramatic near massive compact objects. But they are always present, always measurable, always consistent. At this point, gravity stops being something added to physics. It becomes something foundational. It determines how motion is defined. It determines how time is compared. It determines how distance is measured. This is why gravity has resisted unification with other interactions. Other forces act within space-time. Gravity shapes space-time itself. It refuses to be placed alongside forces that assume a fixed background. And this is why gravity remains misunderstood. Everyday language treats it as an influence layered on top of reality. Physics shows that it is woven into reality from the start. By the time measurements have led us here, gravity is no longer familiar. It is no longer intuitive. It is not even optional. Remove gravity and the structure of space and time collapses with it. The challenge ahead is not to explain falling. It is to understand why the universe has the geometry it does and why matter and energy dictate that geometry in the precise way they do. This is where the modern story of gravity truly begins. Long before gravity became a measured problem, it was a story built from observation without instruments, from reasoning without experiments, from intuition stretched as far as it could go. For most of human history, gravity was not something to be quantified. It was something to be explained in words. The earliest explanations did not begin with falling objects. They began with purpose. In the ancient world, motion was not treated as neutral. Things moved because they sought their proper place. Stones fell because they belonged to the earth. Fire rose because it belonged to the sky. The universe was ordered, layered, and meaningful. Motion was not just motion, it was fulfillment. This framework was not careless, it was internally consistent. It matched everyday experience remarkably well. Heavy objects did fall faster in air, flames did rise, smoke did drift upward. The ground did feel like the natural resting place of solid things. There was no reason, from within ordinary experience, to doubt this picture. Within this worldview, gravity was not a force at all. It was a tendency, a natural inclination of matter to return home. Objects did not need to be pushed or pulled. They simply moved toward where they belonged. The earth was the center because everything fell toward it. The heavens were different because celestial objects did not fall. They moved in perfect circles, endlessly, without decay. This division between the earth and the sky shaped physics for centuries. What happened below the moon followed one set of rules. What happened above it followed another. Falling apples and orbiting planets were not related phenomena. They belonged to different realms governed by different principles. This separation felt obvious. The sky did not behave like the ground. The stars did not fall. The planets traced smooth, repeating paths. Nothing in everyday life suggested they should be treated the same way. The limitation of this approach was not ignorance, it was methodology. These early models did not rely on controlled experiments. They relied on reasoning from appearances. If something matched what people saw and felt, it was considered adequate. There was no systematic way to isolate variables, to remove air resistance, to test assumptions. by forcing nature into artificial conditions. Because of this, certain questions were never asked. Why do objects of different mass fall together when air is removed? Why does motion persist in the absence of resistance? Why should circular motion require continuous cause? These questions only arise when intuition is challenged deliberately. The ancient framework was not foolish. It was incomplete. It worked within the narrow domain of untested experience, but it could not scale beyond it. As observations improved, cracks began to appear. Astronomers tracked planetary motion with increasing precision. The paths were not perfect circles. They deviated, they shifted. Predictions drifted over time. Small errors accumulated. To preserve the old model, increasingly complex adjustments were added. Circles within circles, corrections layered on top of corrections. The system grew elaborate, but not deeper. It described motion without explaining it. What was missing was a shift in attitude, a willingness to let nature contradict expectation, a commitment to measurement even when results felt wrong, a readiness to abandon explanation by purpose in favor of explanation by law. That shift did not happen quickly. It required new tools, new mathematics, and a new idea of what knowledge itself should look like. Physics had to move away from asking why things seek their place, and toward asking how things move under precise conditions. This transition marked the birth of experimental physics. Motion became something to be timed, measured, compared. Falling objects were no longer symbols. They became data. Once this shift occurred, gravity stopped being a story about belonging. It became a problem of motion, and the universe began to reveal patterns that intuition alone could never have uncovered. As experimentation slowly entered the study of motion, gravity began to lose its philosophical shelter. Simple questions produced uncomfortable answers. What happens if two objects fall in the absence of air? What happens if motion is observed not casually, but carefully, timed and repeated? What happens when expectations are ignored and results are recorded exactly as they appear? The answers did not agree with ancient ideas. Objects did not fall according to purpose. They fell according to rules that did not care what the objects were made of. A stone and a piece of wood behaved the same way when stripped of resistance. Motion no longer required an explanation rooted in intention. It required numbers. One of the most disruptive ideas was that motion does not require continuous cause. In everyday experience, things stop moving unless they are pushed. Carts slow, arrows fall. But this is not because motion fades naturally. It is because resistance is everywhere. Air drags, surfaces scrape, energy leaks away. When resistance is removed, motion persists. An object already moving keeps moving. No force is required to maintain it. This idea feels obvious now, but it was revolutionary at the time. It shattered the belief that rest was the natural state of matter. Motion itself became neutral, neither special nor unstable. This shift forced gravity into a new role. If objects do not naturally come to rest, then falling must be explained as a deviation from straight motion, not a return to it. Gravity becomes something that changes motion, not something that completes it. The ancient framework had no place for this idea. It treated rest as fundamental and motion as something that needed explanation. Experimental results reversed this logic. Motion became the default, acceleration became the mystery. As instruments improved, measurements grew more precise. Time could be divided into smaller and smaller intervals. Distances could be compared more accurately. Patterns emerged that could not be dismissed as coincidence. Falling objects followed consistent mathematical relationships. The same relationships appeared again and again. These regularities demanded a new kind of explanation. Not a story about purpose, but a law that applied universally. A rule that held whether the object was a stone, a planet, or a droplet of water. Gravity began to look like something that acted everywhere, not just near Earth. The division between the sky and the ground started to collapse. If the same principles governed falling apples and moving moons, then celestial motion was no longer sacred or separate. The heavens obeyed the same rules as the earth. This realization was deeply unsettling. It removed humanity from the center of a privileged cosmic arrangement. Earth was no longer the unique anchor of motion. It became one body among many, subject to the same laws as everything else. Pre-scientific models could not survive this transition intact. They were not designed to accommodate universality. They explained specific experiences in specific contexts. They were never meant to scale outward to the entire cosmos. The failure of these models was not a failure of intelligence, it was a failure of tools. Without controlled experiments, without precise timing, without a mathematical language capable of expressing change continuously, gravity could not be captured accurately. Once those tools arrived, intuition was no longer enough. Gravity had to be redefined not as a tendency, not as a desire, not as a property of heaviness, but as a relationship that could be written down, tested, and predicted. The stage was set for a transformation. Gravity was about to become something radically different. Not a story about where things belong, but a law describing how everything moves. The final collapse of the old framework did not happen because it was disproven in a single moment. It happened because it stopped being useful. As measurements accumulated, as predictions were tested against reality, pre-scientific ideas could no longer keep pace. They explained too little and required too much adjustment to survive. What replaced them was not immediately a new theory of gravity, but a new standard for truth. Explanations were no longer judged by how natural they felt or how elegant they sounded. They were judged by how well they matched observation. If a prediction failed, the explanation was weakened. If it failed repeatedly, it was abandoned. This change was subtle but irreversible. Physics became anchored to experiment. Motion was described using quantities that could be measured and compared. Time became something that could be counted. Distance became something that could be subdivided. Change itself became mathematical. Gravity entered this new framework reluctantly. It resisted simple description. It produced motion that looked uniform, but concealed deeper structure. Objects accelerated smoothly, but the reason for that smoothness remained unclear. Still, the behavior itself could be captured with increasing accuracy. Once gravity was treated as a universal influence rather than a local tendency, the cosmos became unified. The same rule that governed a falling object applied to the motion of the moon. The same relationship that described a stone dropping described a planet tracing its path across the sky. This unification did not require new assumptions about purpose or hierarchy. It required only that the same measurements be applied everywhere. Earth lost its special status. The heavens lost their exemption. Nature became consistent. Pre-scientific models could not survive this leveling. They depended on distinction between up and down, between earth and sky, between natural and unnatural motion. Experimental physics erased those boundaries. What remained was a problem that was both clearer and more difficult. Gravity could now be described with precision, but not yet explained. The numbers worked. The predictions improved. But the underlying cause remained hidden. This marked the end of gravity as a philosophical idea and the beginning of gravity as a physical law. It was no longer something inferred from meaning. It was something extracted from data. The next step would give gravity extraordinary predictive power. It would allow physicists to calculate motion across the solar system and beyond. It would turn gravity into one of the most successful descriptions in the history of science. But it would also deepen the mystery, because even as gravity became precise, it remained conceptually unresolved. When gravity entered mathematics, it did not lose its mystery, it gained discipline. For the first time, gravity could be written down in a way that allowed precise calculation, not just description after the fact, but prediction in advance. This marked a turning point in the history of physics, because gravity became something that could be tested far beyond everyday experience. The core idea was deceptively simple. Every object with mass influences every other object with mass. This influence does not depend on what the objects are made of. It depends only on how massive they are and how far apart they are. The greater the mass, the stronger the influence. The greater the separation, the weaker the influence. What made this idea revolutionary was not that it sounded reasonable, but that it worked. When applied to the motion of planets, the same rule explained why they follow their observed paths. When applied to the Moon, it explained why it remains bound to Earth instead of drifting away. When applied to objects near the surface of Earth, it reproduced the measured acceleration of falling bodies. For the first time, the same mathematical relationship connected falling apples and orbiting worlds. Gravity became universal in the strongest possible sense. One law applied everywhere. The influence of gravity weakened with distance in a very specific way. If the distance between two objects doubled, the gravitational effect became 4 times weaker. If the distance tripled, the effect became 9 times weaker. This precise pattern appeared again and again in observation. It was not chosen for elegance, it was inferred from data. With this rule in hand, physicists could calculate motion with extraordinary success. Planetary positions could be predicted years in advance. Tides could be understood as the combined gravitational influence of Earth and the Moon. The behavior of comets could be traced across long arcs through the solar system. The power of this description was undeniable. It transformed astronomy from a catalogue of observations into a predictive science. The sky was no longer a mystery to be interpreted. It became a system to be calculated. And yet, something important was missing. The mathematical description worked, but it did not explain how gravity acted. It specified the strength of the interaction, but not its nature. It told physicists what gravity does, but not what gravity is. This was not an oversight. It was a conscious decision. The focus was on accuracy, not mechanism. If a rule predicted motion correctly, it was accepted, even if the underlying cause remained unknown. In fact, there was deep discomfort with the idea that gravity acted across empty space without mediation. How could one object influence another instantly across vast distances? How could a planet affect another planet without anything connecting them? This problem was not ignored. It was acknowledged openly. The mathematical framework did not pretend to offer a physical mechanism. It offered only a relationship that matched observation. And that was enough to change science forever. For the first time, gravity could be treated as a precise input to calculation. Its effects could be isolated, combined, and tested. Errors could be measured. Predictions could fail or succeed clearly. Gravity became empirical power embodied in mathematics, but the very success of this approach would soon expose its limits. The more this mathematical description was used, the more astonishing its reach became. With the same equation, physicists could describe the fall of an object from a tower and the motion of a planet across the sky. No separate rule was needed for the heavens. No special exemption was required. The universe appeared unified under a single gravitational law. This success reshaped how knowledge itself was judged. A theory no longer needed to explain underlying causes to be accepted. It needed to predict outcomes correctly. Gravity did not have to reveal its mechanism. It only had to deliver accurate numbers. And it did, again and again. Eclipses could be forecast with precision. The return of comets could be anticipated decades in advance. Subtle irregularities in planetary motion could be traced to the gravitational influence of unseen bodies. Entire planets were discovered not by observation first, but by calculation. Gravity pointed to their existence before telescopes confirmed them. This predictive power was unprecedented. It suggested that the universe operated according to strict universal rules that could be uncovered through mathematics. Gravity became the clearest example of this principle. Yet beneath this triumph lay an unresolved tension. The mathematical law assumed that gravitational influence acted instantly. If one object moved, the effect was felt everywhere immediately. There was no delay, no propagation time. The influence was simply there. This idea was deeply troubling. It conflicted with emerging views about causality and interaction. In every other known process, influences traveled through space. Sound required air. Light traveled at a finite speed. Forces were expected to act locally, transmitted from one place to another. Gravity refused to conform. There was no medium, no signal, no delay. The law worked as if distance did not impose a time cost. For calculations, this posed no immediate problem, but conceptually, it was unsettling. The discomfort was not philosophical. It was physical. Instantaneous influence threatened the consistency of cause and effect. It suggested that information could travel infinitely fast. This clashed with later discoveries about the nature of light and the limits of signal propagation. And yet, abandoning the law was impossible. Its accuracy was overwhelming. The universe behaved as if gravity followed this rule, regardless of how uncomfortable the implication might be. This created a strange divide. Gravity was treated as a perfectly reliable tool and a deeply unsatisfying explanation at the same time. Physicists used it daily while openly admitting they did not understand its nature. This honesty is important. Gravity was never claimed to be fully explained. It was claimed to be accurately described. That distinction allowed physics to move forward without pretending to know more than it did. As measurements improved, the law continued to hold. From the motion of moons to the structure of the solar system, gravity behaved exactly as predicted. The simplicity of the rule hid its depth. A single mathematical relationship accounted for an astonishing range of phenomena, but nature was not finished testing it. As observations reached higher precision, small discrepancies began to appear. Tiny deviations that could not be ignored. Effects so small they escaped early detection, but so consistent they demanded attention. The law that had unified the cosmos was about to encounter its limits. The discrepancies were subtle. They did not announce themselves as failures. They appeared as small mismatches between prediction and observation, so small that they could be dismissed at first as measurement error. But as instruments improved and data accumulated, these mismatches persisted. One of the most important lessons of physics is that tiny errors matter. When a theory is correct, errors shrink as measurements improve. When a theory is incomplete, errors remain. Gravity began to show signs of incompleteness. The most striking issue was not immediately visible in everyday motion. It emerged in the precise tracking of planetary orbits. The paths of planets were not perfectly stable. They shifted slowly over time. Most of these shifts could be explained by the gravitational influence of other planets. But one effect resisted explanation. The orbit of Mercury behaved strangely. Its closest approach to the Sun drifted slightly with each orbit. This drift could be measured. It could be predicted partially. But a small portion remained unexplained. The discrepancy was tiny, far smaller than what intuition could detect, but it was real. Attempts were made to explain it within the existing framework. Perhaps there was unseen matter. Perhaps the Sun was not perfectly shaped. Perhaps another planet existed closer in. Each possibility was examined carefully. None fully resolved the problem. This was not the first time gravity had hinted at unseen influences. In other cases, discrepancies had led to discovery. Entire planets had been inferred from gravitational effects alone. But here, no hidden mass could account for the behavior. The numbers refused to align. At the same time, a deeper conceptual issue remained unresolved. The idea of instantaneous influence grew increasingly uncomfortable as physics advanced. Experiments with light revealed that signals travel at a finite speed. Cause and effect were constrained by time. No interaction could propagate faster than light. Gravity stood apart. Its mathematical description assumed infinite speed. This was not a small technical detail. It conflicted with the emerging structure of physical law. The problem was no longer whether the gravitational law worked. It clearly did. The problem was whether it could coexist with a deeper understanding of space, time, and causality. This placed gravity in a strange position. It was both extraordinarily successful and fundamentally incomplete. It described motion with unmatched accuracy, yet it rested on assumptions that physics was beginning to reject. The success of the theory had delayed its replacement. There was no pressing practical reason to abandon it. Engineers, astronomers, and navigators could rely on it confidently. For most purposes, it was perfect. But physics does not stop at usefulness. It seeks consistency. As understanding of motion and light deepened, gravity began to look less like a force acting within space and more like something that challenged the very nature of space and time. The unexplained discrepancies were not random errors. They were hints that the framework itself was limited. The law of gravity had unified the universe under a single mathematical rule. That achievement would never be undone. Any future theory would have to reproduce its successes, but it would also have to go beyond it. The stage was set for a radical shift. Gravity would be reinterpreted, not replaced. Its equations would survive, but their meaning would change. The most successful description of gravity in history had reached the edge of its domain. The realization that a theory works does not mean it is complete. Physics learns this lesson repeatedly. A description can be accurate within a wide range of conditions and still fail when pushed far enough. Gravity was no exception. Its mathematical power had unified the heavens and the earth, but precision slowly revealed where that power weakened. The problem was not dramatic. Objects did not suddenly behave unpredictably. Planets did not veer off course. The discrepancies were quiet, persistent, and precise. They appeared only when measurements became exact enough to expose them. One limitation emerged from motion itself. The gravitational description assumed that influences acted instantaneously. Distance imposed no delay. If the position of a massive object changed, the gravitational effect was assumed to change everywhere at the same moment. This assumption had worked well enough when speeds were small and distances were moderate. But as physics confronted the nature of light, this assumption became untenable. Experiments revealed that light travels at a fixed speed. No signal can exceed it. This speed is not a property of light alone. It is a limit woven into the structure of space and time. Cause cannot outrun it. Information cannot bypass it. Gravity, as it was written, ignored this limit entirely. It treated space as if it were instantaneous. This created a contradiction. Either gravity violated the deepest constraints of causality, or the theory describing it was incomplete. Another limitation appeared when velocities grew large. The equations assumed that motion could be added and compared in simple ways. But experiments with fast-moving particles showed that time itself depends on speed. Clocks moving relative to one another do not agree. Lengths contract. Simultaneity breaks down. The gravitational framework had no place for these effects. It assumed absolute time and rigid space. Those assumptions worked at everyday speeds. They failed when motion approached the speed of light. Gravity also struggled in strong fields. Near massive objects, predictions became less reliable. The equations produced results, but there was no guarantee they reflected reality. Without experimental access to extreme conditions, these predictions remained untested. The most famous limitation remained the unexplained motion of Mercury. Its orbit continued to drift in a way that resisted all Newtonian explanations. The discrepancy was small, but stubborn. It did not grow or shrink with better data. It remained fixed. This persistence mattered. Physics does not demand perfection from theory. It demands consistency. When a deviation refuses to disappear, it signals that something fundamental is missing. None of this erased the success of the gravitational law. It remained extraordinarily accurate within its domain. It still governs spacecraft navigation. It still predicts tides. It still describes motion across much of the solar system with remarkable precision. But its limitations were now clear. It assumed instantaneous influence. It assumed absolute time. It assumed a static background for motion. These assumptions were increasingly incompatible with what experiments revealed about reality. Gravity was not wrong. It was incomplete. The challenge was not to discard it, but to understand why it worked so well where it did, and why it failed where it did not. Any deeper theory would need to preserve its successes while resolving its contradictions. The cracks in the framework were narrow, but they ran deep, and through them, a new understanding of gravity would emerge. As physicists confronted these limitations, a pattern began to emerge. Every failure of the gravitational law pointed to the same underlying issue. Space and time were being treated as fixed, passive backgrounds. Motion unfolded within them, but they themselves were assumed to remain unchanged. This assumption had gone unquestioned for centuries. Now it was becoming impossible to defend. The problem was not only that gravity acted instantaneously, it was that the very idea of instantaneity was breaking down. Experiments showed that there is no universal present moment shared by all observers. Events that appear simultaneous to one observer are not simultaneous to another. Time itself depends on motion. If time is not absolute, then a force that assumes absolute time cannot be fundamental. Gravity, as it was written, depended on a single universal clock ticking identically everywhere. But nature did not behave that way. Similarly, space was no longer rigid. Measurements of length depended on motion. Distances contracted at high speeds. Geometry itself appeared to be observer-dependent. The background in which gravity acted was no longer stable. This placed gravity in a conceptual trap. Its equations assumed a structure of reality that experiments had already overturned. Yet abandoning those equations outright would mean discarding one of the most successful tools physics had ever created. The tension was unavoidable. Gravity worked too well to ignore. But it rested on assumptions that no longer held. Attempts were made to patch the framework. Corrections were added. Small adjustments were introduced to account for observed discrepancies. But these fixes were cosmetic. They treated symptoms, not causes. The deeper conflict between gravity and the nature of space and time remained unresolved. The unexplained motion of Mercury became a symbol of this conflict. It was not just an anomaly, it was a message, a reminder that even the most successful theories carry the seeds of their own limitations. Gravity was revealing something important. It was not merely another force acting within space-time. It was entangled with space-time itself. The way objects moved could not be separated from the structure through which they moved. This realization required a shift far more radical than modifying an equation. It required rethinking what space and time actually are. Not as fixed containers, but as dynamic participants in physical processes. At the time, this idea was deeply unsettling. Space and time had always been treated as the stage on which physics played out. Now the stage itself seemed to be part of the play. The failures of Newtonian gravity did not diminish its legacy. They elevated it. They showed how far careful measurement and mathematical discipline could carry understanding, and where new ideas were required. Gravity had reached the boundary of classical physics. Beyond that boundary, familiar concepts would no longer survive unchanged. What lay ahead was not a refinement, but a redefinition. Gravity would be reimagined, not as an invisible force reaching across space, but as something inseparable from space and time themselves. The final confirmation that the classical picture had reached its limit came not from a single dramatic failure, but from the growing weight of incompatibility. Each new experiment that clarified the nature of motion and time made the old assumptions harder to defend. Space could no longer be treated as rigid. Time could no longer be treated as universal. and gravity could no longer be treated as something that simply acted within them. The contradiction was structural. Newtonian gravity required a fixed background in order to define distance and time consistently everywhere, but experiments had already shown that distance and time depend on motion. There was no longer a single framework in which gravitational influence could be applied without ambiguity. Even worse, the theory could not explain why inertial motion and gravitational motion were so deeply connected. The equality between inertial mass and gravitational mass had been confirmed with extraordinary precision. Objects resisted acceleration in exact proportion to how strongly gravity acted on them. This was not predicted. It was observed, and within the classical framework, it was a coincidence without explanation. Coincidences of this kind are dangerous in physics. When two quantities match exactly without reason, it usually means they are not truly separate. It suggests that the distinction itself is artificial. The classical picture insisted that inertia and gravity were different concepts. One described resistance to motion, the other described attraction between masses, and yet nature treated them as identical in effect. The theory could not explain why. This was not a minor flaw. It pointed to a deeper unity that the equations could not capture. At the same time, the assumption of instantaneous gravitational influence became increasingly incompatible with the structure of causality. If no signal can travel faster than light, then gravity could not act instantly across space. Either gravity violated this limit, or the way gravity was being described was fundamentally wrong. The more carefully these issues were examined, the clearer the conclusion became. Gravity was not failing because it was inaccurate. It was failing because it was being asked to do something it was never designed to do. It was being pushed beyond the conceptual framework that supported it. Within its proper domain, the theory remained extraordinarily reliable. For weak gravitational fields and low speeds, it continued to match observation with remarkable precision. It still does. But outside that domain, its foundations cracked. Physics had reached a crossroads. One path involved clinging to a familiar picture and accepting unresolved contradictions. The other required abandoning deeply held assumptions about space and time themselves. The second path was far more difficult. It demanded a willingness to let go of absolute time, rigid space, and instantaneous influence. It demanded a new way of thinking, one that placed geometry at the center of physical law. Gravity had led physics to this point not through speculation, but through evidence. Each limitation was revealed by measurement. Each contradiction was exposed by precision. Nothing was forced. Nothing was imagined. The classical theory of gravity had done its job. It had unified motion across the universe. It had demonstrated the power of mathematical law. And in doing so, it had shown exactly where it could no longer go. The next step would not discard its achievements. It would explain why they worked so well, and why they failed when they did. Gravity was about to be understood not as a force, but as something far more fundamental. When gravity finally broke free from the limits of classical thinking, it did not do so by adding a new force or inventing a hidden mechanism. It did so by changing the question entirely. Instead of asking what force pulls objects together, physics began asking why objects move the way they do in the first place. The starting point was deceptively simple. If an observer in free fall feels no gravity, then free fall must represent a natural state of motion. Not motion under influence, but motion without interference. This observation alone overturns centuries of intuition. It means that gravity does not announce itself as a force acting on objects. It disappears the moment objects are allowed to move freely. This idea was not philosophical. It was empirical. No experiment performed inside a freely falling system can detect gravity locally. The laws of physics inside such a system reduce to those of ordinary motion in empty space. Gravity vanishes from the equations. This fact carries enormous weight. If gravity can be transformed away locally by choosing the right frame of motion, then it cannot be an ordinary force. Forces do not disappear when you change perspective. They act regardless of how you move. the equality between inertial mass and gravitational mass now took on new meaning. It was no longer a coincidence, it was a clue. It suggested that resistance to acceleration and response to gravity were not two separate properties at all. They were expressions of the same underlying structure. The key insight was this: objects are not being pulled off straight paths by gravity. They are following straight paths in a geometry that is not flat. What appears to us as acceleration is actually the result of motion through curved space-time. This is where gravity changes identity. It stops being something that acts within space and time. It becomes something that shapes space and time themselves. Space-time is not a backdrop. It is a physical entity with measurable properties. Distances and durations depend on how space-time is shaped. Mass and energy determine that shape. Motion responds to it automatically. An object in free fall follows the straightest possible path through space-time. That path is called a geodesic. It is not straight in the everyday sense, but it is straight in the geometric sense. No force pushes the object along it. The object simply moves as space-time allows. This explains why free fall feels weightless. There is no force acting on the object. There is only geometry guiding its motion. Weight appears only when motion is constrained. When the ground prevents an object from following its natural path, the object accelerates relative to space-time. That acceleration is what produces force and sensation. Gravity is no longer something that causes acceleration. Acceleration is what reveals deviation from gravity. This shift resolves the contradictions that plagued the classical picture. There is no instantaneous influence traveling across space. Changes in space-time geometry propagate at finite speed. Causality is preserved. Time is no longer absolute. It flows differently depending on gravitational conditions. Clocks near massive objects tick more slowly because space-time itself is structured differently there. Light bends not because it has weight, but because it follows the geometry of space-time. Orbits arise not from invisible pulls, but from paths shaped by mass and energy. These effects are not philosophical interpretations. They are measured. Light from distant stars bends as it passes near massive bodies. Clocks at different heights tick at different rates. Signals exchanged between satellites and Earth must account for gravitational time differences to remain accurate. The equations that describe this relationship between mass, energy, and geometry are complex. They do not describe forces. They describe how space-time curves in response to what it contains, and how motion responds to that curvature. Gravity, in this picture, is geometry made physical. And remarkably, this geometric theory reproduces all the successes of classical gravity in the domain where classical assumptions hold. Where gravitational fields are weak and velocities are low, the curved geometry becomes nearly flat. The old equations reappear as approximations. This was not guaranteed. It was demanded by consistency. Any new theory had to explain why the old one worked as well as it did. General relativity did exactly that. It did not discard classical gravity. It explained it. General relativity did not arrive as an abstract philosophical leap. It emerged because measurement left no other option. Every piece of evidence that strained the classical picture found a natural place within this new geometric framework. What once looked like contradictions became consequences. One of the first confirmations came from light itself. If space-time is curved by mass, then light must follow that curvature. Light does not slow down or speed up. It always moves at the same speed locally, but its path bends because the geometry it moves through is not flat. This prediction could be tested. During a solar eclipse, stars near the edge of the sun appear slightly displaced from their usual positions. The light from those stars passes close to the sun before reaching Earth. Measurements showed that the light was deflected by exactly the amount predicted by curved space-time. Not approximately, precisely. This was not an interpretation layered onto the data. It was a direct comparison between prediction and observation. Gravity was bending light, not by pulling on it, but by shaping the space through which it traveled. Time provided another test. If space-time geometry changes near mass, then time itself must flow differently. Clocks closer to massive objects should tick more slowly than clocks farther away. This effect is small near Earth, but it is measurable. Atomic clocks placed at different heights do not remain synchronized. The difference accumulates exactly as predicted. These effects are not confined to laboratories. They are built into modern technology. Satellite systems must correct for gravitational time differences to function accurately. Without those corrections, navigation errors would grow rapidly. The system would drift out of alignment. This is not theoretical elegance, it is practical necessity. General relativity also explained the long-standing puzzle of Mercury. The small, unexplained drift in its orbit emerged naturally from space-time curvature near the Sun. No extra planets were required, no hidden forces. The discrepancy vanished. What had once been an anomaly became confirmation. The theory did something more profound as well. It unified gravity with the structure of motion itself. There was no longer a need to distinguish between inertial motion and gravitational motion. They were the same thing, viewed differently. Freefall was not motion under force. It was motion along the natural geometry of space-time. This removed the mysterious coincidence between inertial mass and gravitational mass. They were not separate properties that happened to match. They were reflections of a single underlying principle. Objects resist acceleration away from the paths that space-time defines. Gravity was no longer something added to motion. It defined motion. The universe in this picture is not passive. Space stretches and curves. Time slows and accelerates. Mass and energy tell space-time how to shape itself. Space-time tells matter how to move. This relationship is not metaphorical. It is encoded in equations that relate geometry to physical content. Those equations are difficult, but their meaning is clear. Geometry is dynamic. It responds. Importantly, general relativity does not claim to explain everything. It does not explain why space-time exists. It does not explain why mass curves it in the way it does. It describes the relationship accurately and completely within its domain. And within that domain, it has passed every test so far. From the bending of light to the ticking of clocks to the motion of planets, gravity behaves exactly as curved space-time predicts. Where classical gravity approximates reality, general relativity reproduces it. Where classical gravity fails, general relativity succeeds. This is not coincidence. It is evidence that gravity is not a force layered onto the universe, but a property of the universe itself. As the implications of this geometric picture settled in, gravity began to look less like an interaction and more like a framework. It was no longer something acting within the universe. It was part of what the universe is. Motion, time, and distance were not merely influenced by gravity, they were defined through it. This realization changed how physicists understood prediction itself. In classical gravity, one specifies forces and calculates resulting motion. In general relativity, one specifies mass and energy, determines the geometry that results, and motion follows automatically. There is no need to ask what force causes an object to move. The object is simply tracing the structure of space-time. This difference matters. It means gravity does not need a carrier or a medium. There is no gravitational substance flowing through space. There is no signal that must be transmitted instantaneously. Changes in space-time geometry propagate at finite speed, respecting the same causal limits as light. Gravity becomes compatible with the deepest principles of relativity. It also means gravity cannot be turned off locally by shielding or cancellation. You cannot block space-time geometry. You can only move through it. Gravity is not something that can be screened or isolated. It is inseparable from the environment itself. The theory makes predictions far beyond everyday experience. It predicts that time slows dramatically near extremely dense objects. It predicts that paths of light can loop and focus. It predicts that orbiting systems lose energy by emitting ripples in space-time itself. All of these predictions arise naturally from the equations, not from added assumptions. What makes this remarkable is not that the theory is mathematically sophisticated, but that its predictions are restrained. It does not invent new effects without necessity. Every consequence follows from the same core idea. Geometry responds to mass and energy. Motion responds to geometry. Where gravity is weak, space-time is nearly flat. In these regions, motion looks almost classical. The old equations reappear as approximations. This explains why classical gravity worked so well for so long. It was never wrong within its proper limits. It was incomplete. Where gravity is strong, the geometry departs sharply from flatness. Time slows. Paths curve dramatically. The difference between prediction and intuition grows larger, but the rules remain the same. There is no special case, only geometry changing smoothly with conditions. General relativity does not replace gravity with mystery. It replaces intuition with structure. It does not claim to explain why the universe has this relationship between mass and geometry. It claims only that this relationship exists and can be measured. And measured it has been. Every test so far has reinforced the same conclusion. Gravity behaves exactly as a geometric property of space-time should. No experiment has yet contradicted this picture within the range it claims to describe. This does not mean the story is finished. It means the foundation is solid. Gravity, once thought of as a simple pull, has revealed itself as a guide to the deepest architecture of reality. By following its measurements, physics was forced to rethink space and time themselves. And in doing so, it uncovered a theory that is not only powerful, but precise. A theory that explains why gravity feels invisible in free fall, why time flows unevenly, and why motion follows paths that no force could easily produce. General relativity did not solve every problem, but it solved the right ones. General relativity transformed gravity from a force into geometry, and in doing so, it resolved contradictions that had troubled physics for centuries. Its predictions matched observation with extraordinary precision. Light bent exactly as expected. Time flowed differently where mass was present. Orbits behaved as curved paths through space-time rather than as the result of invisible pulls. For most situations encountered in nature, the theory worked flawlessly. But success in physics is never the end of the story. Every theory carries within it the conditions under which it must fail. General relativity was no exception. The first signs of trouble appeared not as experimental failures, but as mathematical warnings. When the equations were pushed to extreme conditions, they produced results that no longer made physical sense. Certain solutions predicted infinite curvature, infinite density, and infinite distortion of space-time. These infinities were not measured quantities, they were signals. In physics, infinities are not discoveries, they are alarms. They indicate that a theory has been applied beyond the domain where its assumptions remain valid. These problematic regions became known as singularities. They appear when matter is compressed beyond any ordinary scale. According to the equations, space-time curvature grows without bound. Time slows to a halt. Distances lose meaning. The structure of geometry itself breaks down. Importantly, general relativity does not describe what happens at a singularity. It cannot. The equations stop being predictive. They no longer yield finite answers. This is not because nature becomes undefined, but because the theory runs out of tools. The most well-known context in which singularities arise is the prediction of black holes. When a massive object collapses beyond a certain limit, no known force can halt the contraction. According to the equations, a region forms from which nothing can escape. Not light, not information. The boundary of this region is called an event horizon. It is not a physical surface. It is a geometric boundary in space-time. Crossing it does not produce any local signal or shock. An observer in free fall experiences nothing unusual at the moment of crossing. Gravity remains invisible, and yet, From the outside, the behavior is dramatic. Signals from the infalling object become increasingly delayed. Light is red-shifted. Time appears to slow near the horizon. These effects are not speculative. They are predicted precisely and confirmed indirectly through observation. Black holes were once treated as purely theoretical curiosities. That view is no longer defensible. Astronomical observations reveal compact objects whose behavior matches black hole predictions exactly. Stars orbit unseen massive centers at extreme speeds. Gas heats and emits radiation as it spirals inward. Gravitational waves carry signatures of massive compact mergers. The existence of event horizons is supported by observation. But the singularities they enclose remain beyond description. This distinction is crucial. General relativity predicts black holes reliably up to the horizon. It fails only at the central singularity. The breakdown does not occur where observation ends. It occurs where the theory itself loses meaning. This tells us something important. General relativity is not wrong where it breaks down. It is incomplete. The same issue appears at the beginning of the universe. When the equations are applied backward in time, they predict a state of infinite density and curvature. Time itself appears to begin at a singular boundary. Again, this is not a physical description, it is a mathematical limit. In both cases, the theory signals its own failure. It does not claim to describe these extreme regimes. It merely points to where new physics must enter. Another limitation appears when gravity interacts with quantum phenomena. General relativity treats spacetime as smooth and continuous. Quantum physics reveals that energy and matter behave discretely at small scales. When these two frameworks are forced together, inconsistencies arise. Attempts to describe gravity using standard quantum methods lead to uncontrollable infinities. Predictions lose meaning. The mathematical machinery fails to converge. This is not because gravity behaves strangely, but because the tools being used are incompatible. General relativity assumes a well-defined space-time geometry. Quantum theory assumes fluctuations that destabilize that geometry. The two pictures cannot be reconciled directly. Despite these issues, it is essential to recognize how limited the breakdowns are. General relativity works extraordinarily well across a vast range of scales. From planetary motion to gravitational waves, it remains unmatched. Its failures occur only where conditions are extreme beyond current experimental reach. This is a mark of strength, not weakness. The theory tells us exactly where it stops being reliable. It does not pretend to explain everything. Where general relativity breaks down, it does so honestly. It signals the need for a deeper framework without offering speculation as substitute. Gravity, once again, resists completion. The breakdowns of general relativity do not announce themselves through contradiction with experiment. They appear through silence. The equations cease to speak. They return infinities where physics demands finite answers. This silence is not ambiguity. It is a boundary. Near a singularity, the very quantities that define space-time lose meaning. Distance cannot be defined because geometry diverges. Time cannot be extended because the equations cannot advance it further. Cause and effect, which rely on ordered time, no longer apply. The framework dissolves. This does not mean nature becomes chaotic or unknowable. It means the mathematical language being used is no longer appropriate. General relativity assumes smoothness. It assumes continuity. It assumes that space-time can be divided into arbitrarily small regions without altering its character. Near singularities, this assumption fails. Black holes provide a clear example. Everything observable about them behaves exactly as the theory predicts. The orbits of nearby stars, the radiation emitted by infalling matter, the gravitational waves produced when two black holes merge. All of these match calculations with astonishing accuracy. But none of these observations probe the singularity itself. They probe the space-time outside it. And there, general relativity performs perfectly. The event horizon marks a critical distinction. It is not a place where physics breaks. It is a place where information becomes inaccessible to distant observers. The laws remain intact at the horizon. The breakdown lies deeper, where the theory no longer applies. This separation matters. It tells us that black holes are not failures of general relativity. They are confirmations of it, up to the point where its assumptions no longer hold. The same is true for the early universe. Observations of cosmic expansion, background radiation, and large-scale structure are all well described by general relativity. The theory traces the universe back to an extremely hot, dense state. But when it reaches the mathematical singularity at the beginning of time, it stops. That boundary is not an event in time. It is the edge of the theory. It marks where our current description ends, not where existence begins. Physicists are careful about this distinction. The term Big Bang does not describe an explosion in space. It describes a limit in our equations, a point beyond which the framework cannot extend. General relativity does not tell us what came before. It does not tell us how space-time emerged. It does not tell us whether time itself had a beginning. It only tells us that under extreme conditions, curvature becomes so strong that the theory cannot remain predictive. Another signal of incompleteness appears when gravity interacts with quantum systems. Quantum physics treats fields as fluctuating entities. Energy is never perfectly still. Even empty space exhibits variation. General relativity, by contrast, treats space-time as a smooth geometry responding to average energy and momentum. When quantum fluctuations are introduced into space-time geometry, the equations lose stability. Predictions diverge. The smooth background assumed by relativity cannot survive the jitter of quantum behavior. This incompatibility does not show up in everyday experiments. Gravity is extraordinarily weak at quantum scales. Quantum effects dominate, and gravity can be ignored safely. But conceptually, the conflict remains. Physics now stands with two extraordinarily successful frameworks that refuse to merge. One describes the structure of space-time. The other describes the behavior of matter and energy at the smallest scales. Each works perfectly within its domain. Together, they fail. This is philosophical embarrassment. It is a technical one. It tells us that our descriptions are incomplete, not that reality is incoherent. General relativity breaks down where geometry itself becomes unstable, and where quantum fluctuations cannot be neglected. It signals the need for a deeper description that preserves its successes while extending beyond its limits. But that description has not yet been confirmed. Where gravity breaks down, physics becomes quiet again. The recognition of these limits reshapes how general relativity should be understood. It is not a failed theory awaiting replacement. It is a precise map with clearly marked boundaries. Within those boundaries, it performs with unmatched accuracy. Beyond them, it does not speculate. It stops. This restraint is rare in physics. Many theories fail by making incorrect predictions. General relativity fails by refusing to predict where its assumptions collapse. That refusal is a form of honesty. The presence of singularities does not mean that nature contains infinities. It means that smooth geometry is no longer an adequate description. Just as classical physics failed at high speeds and strong gravitational fields, general relativity fails where space-time itself can no longer be treated as continuous. This suggests that space-time may have a deeper structure, one that becomes relevant only at extreme densities and energies, one that smooth geometry averages over but cannot resolve. Importantly, nothing observed so far contradicts general relativity in the regimes where it claims validity. Gravitational waves match predictions exactly. Binary pulsars lose energy at the expected rate. Light bends and time dilates precisely as calculated. Every test reinforces the theory where it applies. The breakdowns are theoretical boundaries, not experimental failures. This distinction matters because it changes how progress must occur. Gravity will not be replaced because it is wrong. It will be extended because it is incomplete. Any deeper framework must reduce to general relativity, where space-time behaves smoothly and quantum effects are negligible. This requirement is severe. It eliminates vast classes of speculative ideas. Only theories that reproduce known behavior exactly while resolving known breakdowns can survive. For now, gravity occupies an unusual position in physics. It is described by a theory that is both extraordinarily successful and fundamentally unfinished. It governs the large-scale structure of the universe, while resisting integration with the physics of the small. General relativity showed that gravity is geometry. Its breakdowns suggest that geometry itself may not be fundamental, or that it may emerge from something deeper. What that deeper structure is remains unknown. It is not hidden by lack of imagination. It is hidden by lack of evidence. Until that evidence appears, general relativity stands as the best description of gravity ever constructed. Its limits do not weaken it, they define it. Gravity, once again, reveals itself not through certainty, but through constraint. By the time general relativity had revealed gravity as geometry, another revolution was already reshaping physics in a very different direction. While gravity explained the large-scale structure of the universe, quantum mechanics was uncovering the rules that govern matter and energy at the smallest scales. Each framework was built from evidence. Each was tested relentlessly. Each worked with extraordinary precision within its domain. And yet, when brought together, they refused to cooperate. Quantum mechanics describes a world that is fundamentally discrete. Energy comes in packets. Fields fluctuate even in their lowest states. Particles do not follow single paths, but explore many possibilities at once. Outcomes are described by probabilities, not certainties. This is not philosophical preference. It is what experiments show. General relativity describes a world that is smooth and continuous. Space-time is a geometric object that can be divided into arbitrarily small regions without losing meaning. Curvature changes gradually. Motion responds to this smooth structure in a deterministic way. Each description is internally consistent. The problem arises when gravity is placed inside the quantum framework. In quantum physics, forces are typically described through fields that can be quantized. These fields have excitations. They exchange energy through discrete interactions. This approach works remarkably well for electromagnetism and the nuclear forces. Predictions match experiments to astonishing accuracy. When the same methods are applied to gravity, they fail. The calculations produce infinities that cannot be removed. Predictions lose stability. The theory stops making sense. This is not because gravity behaves strangely. It is because the assumptions of quantum field theory conflict with the assumptions of general relativity. Quantum theory assumes a fixed background on which fields exist. General relativity insists that the background itself is dynamic. Trying to quantize gravity as if it were just another field requires treating space-time as both fixed and fluctuating at the same time. The mathematics cannot support this contradiction. Experiment offers little guidance here. Gravity is extraordinarily weak at quantum scales. The gravitational influence of a single particle is so small that it cannot be measured with current technology. Quantum effects dominate completely. Gravity can be ignored safely in almost all laboratory experiments. This makes the problem difficult to probe empirically. The regimes where quantum effects and strong gravity coexist are extreme. Near singularities, near the beginning of the universe, inside black holes. These environments are inaccessible to direct experiment. What is known experimentally is limited but important. Quantum systems respond to gravity. Clocks based on quantum transitions experience gravitational time dilation. Particles fall in gravitational fields just like classical objects. These effects are fully described by general relativity applied to quantum matter. What is not known is how space-time itself behaves quantum mechanically. Does it fluctuate? Does it have a smallest scale? Does geometry emerge from something more fundamental? These questions remain open. It is tempting to fill this gap with speculation. Physics resists that temptation. Without experimental evidence, hypotheses remain tentative. No proposed theory of quantum gravity has been confirmed. This incompatibility is not a crisis. It is a boundary. It marks the edge of current understanding. Gravity connects the smooth geometry of space-time with the probabilistic world of quantum mechanics. The connection is real, it is unavoidable, but it is not yet understood. Until it is, gravity remains the only interaction that resists quantization. The incompatibility between gravity and quantum mechanics is often misunderstood as a failure of one theory or the other. It is neither. Both frameworks are supported by overwhelming experimental evidence. The conflict arises not from error, but from depth. Each theory describes reality so well within its own domain that their assumptions collide when those domains overlap. Quantum mechanics treats uncertainty as fundamental. It does not arise from ignorance or incomplete measurement. It is built into the structure of the theory. Even in the lowest energy state, systems fluctuate. Fields are never perfectly still. Energy cannot be pinned down to exact values. This behavior has been confirmed repeatedly in experiment. General relativity, by contrast, treats space-time as a well-defined geometric entity. It assumes that curvature can be specified exactly at every point. Motion follows deterministically from that curvature. There is no room for intrinsic uncertainty in the structure of space-time itself. When these two pictures are forced together, the conflict becomes unavoidable. If space-time geometry fluctuates quantum mechanically, then the very notion of distance and duration becomes uncertain. But quantum theory relies on those notions to define fields, interactions, and measurements. The framework collapses under its own assumptions. Attempts to resolve this conflict have taken many forms. Some approaches try to quantize space-time directly. Others attempt to describe gravity as emerging from more fundamental quantum processes. Still others modify the structure of quantum theory itself. What they share is a lack of experimental confirmation. This absence of evidence is not a weakness of physics. It reflects the difficulty of accessing the relevant regimes. Quantum gravitational effects are expected to become significant only at extremely small length scales or extremely high energies. Conditions far beyond what current experiments can achieve. In everyday situations, the two theories coexist peacefully. Quantum mechanics governs atoms and particles. General relativity governs planets and galaxies. The overlap is minimal. Only in extreme environments do their differences matter. This coexistence has practical consequences. Physicists can use quantum theory to design electronics without worrying about gravity. They can use general relativity to predict planetary motion without worrying about quantum fluctuations. Each theory applies where it is appropriate. But this division is provisional. It reflects the limits of current observation, not a fundamental separation in nature. The universe does not operate according to different rules in different places. There must be a deeper description that contains both frameworks as approximations. What that description looks like is unknown. It may resemble neither quantum mechanics nor general relativity in their current forms. It may require concepts that have not yet been imagined. What matters is not the form of the solution, but the constraints it must satisfy. Any successful theory must reproduce the predictions of quantum mechanics where gravity is negligible. It must reproduce the predictions of general relativity where space-time behaves smoothly. It must explain why gravity is so weak compared to other interactions. And it must do so without introducing contradictions. These requirements are severe. They sharply limit what is possible. This is why progress is slow. Gravity remains the outlier among interactions. It shapes the universe on the largest scales, yet it resists integration into the quantum framework that governs everything else. This resistance is not accidental. It is telling us something profound about the structure of reality. The incompatibility between gravity and quantum mechanics is not a gap in knowledge to be filled casually. It is a signpost pointing toward deeper physics. And until that physics is revealed, gravity remains both understood and incomplete. The unresolved tension between gravity and quantum mechanics has a quiet consequence. It limits what physics can claim with confidence. Without experimental access to the regimes where both frameworks must apply simultaneously, certainty gives way to constraint. Physics proceeds not by guessing what must be true, but by identifying what cannot be avoided. One thing is clear: gravity cannot simply be treated as another quantum field placed on a fixed background. Every attempt to do so has failed mathematically. The infinities that appear are not technical annoyances. They signal a mismatch of assumptions. A framework built on fluctuating fields cannot rely on a geometry that is both dynamic and fixed at the same time. Another thing is equally clear. General relativity cannot be ignored at small scales simply because gravity is weak there. Weak does not mean irrelevant. It means difficult to detect. The structure of spacetime underlies all physical processes. If that structure has quantum properties, then those properties must eventually matter. Experiments have begun to probe the interface cautiously. Quantum systems have been placed in gravitational fields. Their behavior matches predictions. Time dilation affects quantum clocks exactly as it affects classical ones. Quantum particles fall in gravitational fields just like macroscopic objects. These results confirm that gravity couples to quantum matter consistently. What they do not reveal is how spacetime itself behaves quantum mechanically. They do not show whether geometry fluctuates. They do not show whether spacetime has a smallest unit. They do not show how curvature responds to quantum uncertainty. This absence of evidence places strict limits on what can be claimed. It prevents speculation from becoming doctrine. Physics advances by narrowing the space of possibilities, not by filling gaps with imagination. The incompatibility between gravity and quantum mechanics therefore remains an open problem, not a paradox. Both theories work. Both are incomplete. The conflict arises only when each is asked to operate outside its tested domain. Gravity sits at the center of this tension. It is described perfectly as geometry on large scales. It resists quantization at small scales. It links the smooth and the discrete in ways that are not yet understood. This does not mean that gravity is special in a mystical sense. It means it occupies a unique position in the structure of physical law. It connects concepts that were never designed to coexist. For now, physics proceeds cautiously. It builds experiments that push boundaries incrementally. It refines measurements. It tests assumptions. It waits for nature to reveal where current descriptions fail observationally, not just mathematically. Until that moment arrives, gravity remains the one interaction that reminds physics of its limits. It is well described, deeply tested, and fundamentally unfinished. In physics, calling something fundamental does not mean it is simple. It means it cannot be reduced to something else within the framework of known laws. Fundamental interactions are those that appear as basic ingredients in our descriptions of nature, not as consequences of deeper mechanisms. Gravity has long occupied an uneasy place in this classification. On one hand, gravity behaves like an interaction. It influences motion. It governs structure. It acts universally on all forms of energy and matter. On the larger scales, it dominates the architecture of the universe. Stars form because of it. Galaxies hold together because of it. The expansion of the cosmos is shaped by it. On the other hand, gravity does not resemble the other interactions in important ways. Electromagnetism and the nuclear forces act within space-time. They are described by fields that exist on a background. Gravity, in general relativity, is not a field in this sense. It is the background itself. It defines what distance and duration mean. This difference raises a legitimate question. Is gravity fundamental in the same way as other interactions? Or is it a manifestation of something deeper? To approach this question carefully, physics begins with definition. A fundamental interaction is one that cannot be derived from more basic principles within an existing theory. By that standard, gravity is fundamental in general relativity. The geometry of space-time is taken as a primary element. It is not explained further. However, this does not mean that gravity must be fundamental in an ultimate sense. It means only that within our current framework, it is treated as such. There are historical precedents for reclassification. Temperature was once considered fundamental. It is now understood as a statistical measure of microscopic motion. Pressure was once a basic property. It is now derived from particle collisions. In each case, what appeared fundamental at one level emerged from deeper structure at another. This history invites caution. The fact that gravity appears fundamental today does not guarantee that it will remain so. At the same time, caution must apply in the opposite direction as well. The absence of an explanation does not imply the existence of a deeper one. Physics does not assume emergence without evidence. It allows the possibility while demanding restraint. Discussions about gravity as an emergent phenomenon exist in the scientific literature. They explore whether gravitational behavior could arise from underlying statistical or informational principles. These ideas are investigated mathematically. They are debated critically. They are not established. What matters is what is supported by evidence. At present, gravity is measured as a universal coupling between energy and space-time geometry. This coupling has been tested repeatedly. No experiment has shown gravity failing to act universally. No observation has revealed a mechanism beneath it. This universality is itself striking. Gravity does not distinguish between forms of energy. Light gravitates, pressure gravitates. Even vacuum energy appears to gravitate. This suggests a deep connection between gravity and the total content of space-time. Whether this connection is fundamental or emergent remains unresolved. Physics does not yet have the data required to decide. Both possibilities remain open within carefully constrained research. The question, then, is not whether gravity is fundamental in some abstract sense. The question is whether current evidence demands that it be treated as such. So far, it does. If gravity does emerge from deeper physics, that emergence must reproduce general relativity with extraordinary accuracy. It must explain why space-time behaves geometrically. It must account for the universality of gravitational coupling. It must respect all existing tests. These requirements are severe. They eliminate speculation masquerading as explanation. For now, gravity stands as a fundamental interaction in practice, even if its ultimate status remains uncertain. It is treated as basic, not because physics insists on mystery, but because evidence insists on discipline. Gravity remains defined by what it does, not by what we imagine it to be. The difficulty in answering whether gravity is fundamental lies not in lack of theory, but in excess of possibility. Many mathematical constructions can be written down. Very few survive contact with reality. Physics advances by narrowing options through evidence, not by multiplying explanations. When gravity is compared to other interactions, its uniqueness becomes clearer. Electromagnetism acts only on charged particles. The nuclear forces act only at very short distances and on specific constituents of matter. Gravity acts on everything. There are no exceptions. Every form of energy contributes. Every form of mass responds. This universality is not an assumption. It is measured. Experiments show that objects with different compositions fall in the same way. Light bends in gravitational fields. Radiation loses energy climbing out of gravity. Even pressure and stress contribute to gravitational effects. Nothing escapes this coupling. If gravity were emergent, this universality would need explanation. It would not be enough to say that gravity arises statistically or thermodynamically. One would need to show why every form of energy participates identically, without exception. Any deviation would already have been detected. This places strong constraints on alternative ideas. Emergent behavior is common in physics, but it usually comes with limits. Temperature emerges from molecular motion, but only when many particles are involved. Fluid behavior emerges from microscopic interactions, but breaks down at small scales. Gravity shows no such breakdown. It remains universal from laboratory experiments to cosmological observations. Another challenge lies in locality. Fundamental interactions are described locally. They operate through interactions at specific points in space and time. General relativity, despite its geometric nature, preserves locality. Changes in spacetime propagate at finite speed. Cause and effect remain ordered. Any emergent description of gravity must reproduce this locality exactly. It must explain why gravitational influence respects causal limits. It must not allow information to travel faster than light. These are not optional features, they are measured constraints. There is also the question of energy conservation. In general relativity, energy and momentum are linked directly to spacetime curvature. This relationship is precise. It has been tested in systems ranging from binary stars to expanding cosmological models. Any deeper description must preserve this link without approximation. These constraints do not rule out deeper structure. They define what that structure would have to look like. It would need to be subtle, robust, and nearly invisible at accessible scales. It would need to mimic a fundamental interaction with extraordinary fidelity. Because of these demands, physics treats gravity cautiously. It does not elevate speculative ideas to the status of explanation. It does not dismiss them either. It waits. The question of fundamentality therefore remains open, but not ambiguous. Gravity is fundamental in every operational sense. It cannot be derived from known principles. It cannot be turned off. It cannot be isolated. It cannot be reduced. Whether it emerges from something deeper is a question for future evidence, not present belief. For now, gravity continues to define the structure of spacetime itself. And until that definition fails observationally, it remains as fundamental as physics requires. The caution with which physics treats this question reflects experience. Many ideas that seemed compelling at a conceptual level failed under experimental scrutiny. Gravity has endured precisely because it has been constrained by measurement at every step. Its role in shaping spacetime has been confirmed repeatedly across systems that differ wildly in scale and composition. What stands out is not what gravity explains, but what it refuses to explain. It does not offer a mechanism in the classical sense. It does not describe underlying constituents, it describes relationships. Mass and energy determine geometry. Geometry determines motion. That is the entire statement. This economy is not a weakness, it is a sign of maturity. Physics does not add structure without necessity. When a relationship captures all observed behavior, additional layers are not justified. Speculation about deeper origins remains active, but it remains speculation. Without experimental signatures, such ideas cannot be elevated. They may guide research, they may inspire new experiments, but they cannot replace what is known. The universality of gravity remains one of its most striking features. It does not discriminate, it couples to everything that exists within space-time. This suggests that gravity is less like an interaction between objects and more like a property of the environment they inhabit. If gravity is emergent, it would be emergent in an unusual way. It would emerge not from specific constituents, but from the collective behavior of space-time itself. That is a possibility, not a conclusion. What physics can say with confidence is limited but powerful. Gravity behaves exactly as general relativity predicts wherever it has been tested. It governs the motion of planets, the evolution of stars, the dynamics of galaxies, and the expansion of the universe. It shapes time, distance, and causality. Until observations demand otherwise, gravity remains foundational. Its geometric description stands, its universality stands, its limits are known and respected. The question of fundamentality is not a philosophical puzzle. It is an empirical one. It will be answered only when new measurements reveal behavior that cannot be accounted for within the current framework. Until then, Gravity remains what it has always been in physics. Not a mystery to be filled with speculation, but a constraint that shapes everything else. Gravity does not only describe how objects move, it reveals what is present. In many cases, gravity is the only way physics can detect something at all. When matter emits no light, produces no radiation, and leaves no chemical trace, gravity remains the single tool capable of exposing its existence. This is not a theoretical preference, it is an observational necessity. The first signs of a problem appeared when astronomers began measuring how stars move within galaxies. According to the visible distribution of matter, stars far from galactic centers should orbit more slowly than stars closer in. The gravitational influence should weaken with distance. The equations were clear, the measurements were precise, but the stars did not behave as expected. Across many galaxies, stars at large distances moved far faster than visible matter could explain. Their speeds did not decrease. They remained nearly constant across vast regions. This was not a small discrepancy. It was dramatic and consistent. One possible explanation was that the laws of gravity failed on these scales. Another was that additional mass was present, unseen but influential. Physics did not choose between these options arbitrarily, it followed the evidence. Independent measurements supported the second interpretation. Clusters of galaxies exhibited gravitational effects far stronger than visible matter could account for. The motions of galaxies within clusters required additional mass. Again, the discrepancy was too large to ignore. Gravitational lensing provided another line of evidence. Light from distant objects bends as it passes through regions of strong gravity. By measuring this bending, physicists can map the distribution of mass directly, regardless of whether that mass emits light. These maps revealed something striking. The gravitational mass did not align with visible matter alone. Large amounts of mass were present where little or no light could be seen. This mass influenced spacetime geometry without revealing itself electromagnetically. The conclusion was cautious but unavoidable. Gravity was responding to something invisible. This invisible component became known as dark matter. The name describes what is observed, not what is known. It does not imply mystery substance. It implies matter that does not interact with light in detectable ways, but does interact gravitationally. Dark matter is not inferred from a single anomaly. It is inferred from multiple independent observations. Galactic rotation curves, cluster dynamics, gravitational lensing, large-scale structure formation, each points to the same conclusion. The universe contains more gravitational mass than can be accounted for by visible matter alone. Importantly, this inference relies only on gravity. No assumptions are made about the nature of the unseen matter beyond its gravitational influence. Gravity is the measuring instrument. This places gravity in a unique role. It becomes a probe of the unseen. It exposes components of the universe that no other interaction can detect directly. What dark matter is remains unknown. Many possibilities exist. What matters observationally is that something contributes to spacetime curvature without emitting light. That fact is established. Alternative explanations have been considered carefully. Modifications to gravitational law have been proposed and tested. Any such modification must reproduce all known successes of general relativity while explaining galactic and cosmological observations. So far, no alternative has matched the full range of evidence without introducing new problems. This does not mean the case is closed. It means the weight of evidence currently favors additional mass over modified gravity. This conclusion remains open to revision if future observations demand it. Dark matter illustrates something profound about gravity. Gravity does not just govern motion, it reveals structure. It shows us what is present even when nothing can be seen. In this way, gravity continues to challenge intuition. It tells us that most of the universe does not shine, and it does so through measurement alone. The evidence for unseen mass does not rest on any single measurement. It emerges from consistency across scale and method. Wherever gravity is measured carefully, the same pattern appears. There is more mass-shaping space-time than light alone can account for. On the largest scales, this pattern becomes even clearer. When physicists study how galaxies are distributed across the universe, they find structure where none should exist, if only visible matter were present. Galaxies are not scattered randomly. They form filaments, clusters, and vast interconnected networks. These structures require gravitational scaffolding to form. Computer simulations provide a crucial test. When only visible matter is included, structures form too slowly and remain too smooth. The universe does not match observation. When an additional non-luminous component is added, the simulations reproduce the observed large-scale structure with remarkable accuracy. Gravity guides matter into the same patterns seen through telescopes. Again, this conclusion does not depend on assumptions about the nature of dark matter. It depends only on gravity. Gravity determines how matter clumps and evolves. The observed universe behaves as if an invisible gravitational component has been present since early times. Gravitational lensing strengthens this picture further. In some systems, the distribution of gravitational mass is clearly separated from the distribution of visible matter. Colliding galaxy clusters provide dramatic examples. Hot gas emits radiation and marks where visible matter resides. Gravitational lensing reveals where mass is concentrated. The two do not always coincide. These observations are difficult to reconcile without unseen mass. Gravity traces something that does not interact electromagnetically. The geometry responds, regardless of visibility. Dark matter therefore represents not a failure of gravity, but a success. Gravity reveals its presence consistently and independently. It does exactly what it should do. It measures mass through curvature. What remains uncertain is interpretation. Is dark matter a new type of particle? Is it a collection of weakly interacting objects? Is it something more subtle? Physics does not yet know. What physics does know is what dark matter is not. It is not an artifact of poor measurement. It is not confined to a single scale. It is not easily removed by adjusting known parameters. It appears everywhere gravity is measured carefully beyond local systems. The possibility that gravity itself changes behavior on large scales has been explored seriously. Any such change must explain not only galactic rotation, but also lensing, cluster dynamics, cosmic background patterns, and structure formation. This is a demanding requirement. So far, no modification has met it fully without introducing new inconsistencies. This does not close the door. It defines the challenge. Dark matter remains an open problem, not because evidence is weak, but because evidence is strong and specific. It demands explanation, not dismissal. Through dark matter, gravity again reveals its character. It does not tell us what exists by shining light. It tells us by shaping motion and geometry. It exposes what cannot otherwise be seen. Gravity becomes a tool of discovery, not just description. The persistence of this invisible component reshapes how the universe is understood. It suggests that what we see is not what dominates. Stars, gas, and dust account for only a small fraction of the gravitational influence shaping cosmic evolution. The rest is inferred entirely through gravity. This inversion is profound. It means that most of the universe is known not through direct detection, but through its effect on space-time. Gravity becomes the primary sense through which cosmic structure is perceived. Dark matter also clarifies why gravity behaves as it does on large scales. Galaxies do not form in isolation. They grow within gravitational wells created by unseen mass. Visible matter falls into these wells, cools, and ignites into stars. Without this hidden scaffolding, galaxies like the ones we observe would be difficult to explain. This does not mean that gravity itself changes character. It means that gravity is faithfully responding to mass we cannot yet identify. The equations do not fail. They reveal something missing. Importantly, dark matter does not solve every gravitational puzzle. It does not eliminate the need for careful testing of gravity on all scales. It does not end inquiry. It focuses it. It tells physics where to look, not what to believe. The presence of dark matter also reinforces a recurring theme. Gravity is not an intuitive guide to reality. The strongest gravitational influences often come from things that cannot be seen, touched, or directly measured. Gravity does not privilege appearance. It responds to existence. This challenges everyday reasoning. Human intuition evolved to interpret light and contact. The universe operates according to mass and energy. Gravity bridges that gap, revealing structure beyond perception. Whether dark matter consists of particles, fields, or something more subtle remains unknown. What matters is that its gravitational influence is real. It shapes motion. It curves space-time. It leaves fingerprints in observation that cannot be ignored. Future experiments may detect dark matter directly. They may reveal its nature, or they may force a revision of current interpretation. Physics remains open to all outcomes constrained by evidence. For now, dark matter stands as one of the clearest examples of gravity's power to expose the unseen. It reminds us that understanding gravity is inseparable from understanding what exists in the universe. Gravity does not merely pull objects together, it maps reality. Gravity not only governs how matter moves through space, it governs how space itself evolves. On the largest scales imaginable, gravity determines whether the universe slows, coasts, or accelerates. For most of scientific history, it was assumed that gravity must always pull inward, gradually slowing cosmic expansion. That assumption was reasonable. Gravity attracts, matter clumps. Expansion should decelerate under its influence. This expectation followed directly from everything gravity had taught physics before. Then, measurements contradicted it. When astronomers began studying distant stellar explosions as markers of cosmic distance, they expected to see signs of slowing expansion. Instead, they found the opposite. The universe was not decelerating. It was expanding faster over time. This conclusion did not emerge from a single observation. It emerged from many independent measurements that converged on the same result. Distant objects appeared dimmer than expected. Their light had traveled longer through expanding space than models predicted. The expansion history did not match a universe governed by matter alone. Gravity, once again, was the measuring instrument. General relativity allows space-time itself to expand. It also allows that expansion to change over time depending on the total energy content of the universe. When observations revealed acceleration, the equations pointed to a new ingredient, something that contributes to space-time curvature in a way that produces repulsion rather than attraction. This ingredient became known as dark energy. As with dark matter, the name describes what is observed, not what is understood. Dark energy is not detected directly. It is inferred from the behavior of space-time itself. What is measured is simple in concept. Distances between galaxies increase. The rate of increase changes over time. Light from distant sources carries the imprint of this expansion history. From these measurements, physicists reconstruct how the universe has evolved. What is inferred is more subtle. To produce accelerated expansion within general relativity, space-time must contain energy with unusual properties. This energy must remain nearly uniform as the universe expands. Its influence must grow dominant as matter becomes diluted. Dark energy fits these requirements. It behaves as a property of space rather than a substance moving through it. As space expands, the total amount of this energy increases because there is more space for it to occupy. This behavior is counterintuitive. Most forms of energy dilute as space expands. Dark energy does not. Its density remains nearly constant. This constancy is inferred from observation. It is not assumed arbitrarily. Importantly, dark energy does not violate general relativity. It fits within its equations naturally. What it challenges is intuition. It shows that gravity does not always pull inward. Under certain conditions, The geometry of space-time evolves in a way that drives expansion apart. This does not mean gravity has changed. It means the content of space-time includes something with gravitational properties, unlike ordinary matter. What dark energy is remains unknown. It may be related to vacuum energy. It may reflect a property of space-time itself. It may indicate that current understanding is incomplete. Physics does not yet know. What physics does know is what is measured. The expansion of the universe is accelerating. This acceleration is consistent across multiple independent probes. Gravity reveals it through geometry. As with dark matter, alternative explanations have been explored. Modifications to gravity on cosmological scales have been proposed. Any such modification must reproduce all known tests of general relativity, while explaining accelerated expansion. This is a demanding requirement. No alternative has yet met it conclusively. Dark energy, therefore, remains a description, not an explanation. It labels an observed effect within the framework of gravity. It marks a gap in understanding without filling it with speculation. Once again, gravity reveals more than it explains. It shows that the universe is not only expanding, but accelerating. It tells us that most of the energy shaping space-time is invisible. Gravity exposes the limits of knowledge by mapping reality faithfully. The discovery of accelerated expansion forced physics to confront a new aspect of gravity. It showed that gravity does not simply respond to matter in the way intuition expects. It responds to all forms of energy, including those that do not clump, shine, or dilute in familiar ways. In general relativity, gravity is not determined by mass alone. Pressure contributes. Energy density contributes. Even the properties of empty space contribute. The equations do not distinguish between substance and structure. They respond only to what affects space-time curvature. Dark energy enters the theory through this openness. It is not added as a new force. It is included as a form of energy that fills space uniformly. Its gravitational effect is unusual, not because it breaks the rules, but because it follows them precisely. Ordinary matter attracts because its energy density and pressure combine to curve space-time inward. Dark energy behaves differently. Its pressure is negative. This is not a metaphor. It is a mathematical description of how its energy contributes to curvature. The result is expansion that accelerates rather than slows. This does not mean that dark energy pushes galaxies apart in the way a force would. Galaxies are not being repelled through space. Space itself is changing. The geometry between galaxies evolves so that distances grow faster over time. This distinction matters. It preserves causality. No object locally exceeds the speed of light. The expansion occurs in the metric itself, not as motion through space. Gravity remains consistent with relativistic limits. Observations of the cosmic background radiation provide independent confirmation. The pattern of temperature variations imprinted in the early universe encodes information about expansion history. These patterns match a universe that transitioned from matter-dominated deceleration to dark energy-dominated acceleration. Large-scale surveys of galaxies reinforce this picture. The distribution of matter carries the imprint of how structure grew over time. That growth slows as dark energy becomes dominant. The data align with the same expansion history inferred from distant explosions. These independent lines of evidence converge. They do not rely on a single assumption or technique. Gravity ties them together. What remains uncertain is interpretation. Dark energy could be a constant property of space-time. It could evolve slowly over time. It could signal that general relativity requires modification on the largest scales. Current data constrain these possibilities, but do not eliminate them. Importantly, gravity does not fail in any of these scenarios. The equations remain valid. What changes is how their solutions are interpreted. Physics remains careful here. Dark energy is not treated as an explanation of origin. It is treated as a parameter that captures observed behavior. Its value is measured. Its effects are modeled. Its nature remains open. This restraint reflects experience. Premature conclusions have failed before. Gravity has taught physics repeatedly that intuition misleads and measurement constrains. The accelerated expansion of the universe therefore stands as another lesson. Gravity does not guarantee that attraction dominates. Geometry responds to energy in ways that can surprise even the most careful reasoning. Through dark energy, gravity reveals that space-time itself is dynamic on the largest scales. It evolves according to content that cannot be seen, only inferred. The universe is not merely expanding, it is changing how it expands. And gravity is how we know. The implications of accelerated expansion extend far beyond cosmology. They reshape how gravity is understood as a global phenomenon. Gravity does not merely bind systems together, it governs the evolution of space-time itself. Its influence is not limited to local motion. It determines the fate of the universe. As dark energy becomes dominant, the growth of structure slows. Galaxies that are gravitationally bound remain together. Larger structures cease to form. Beyond a certain scale, expansion overwhelms attraction. Regions of the universe become increasingly isolated from one another. This behavior is not speculative. It follows directly from measured expansion rates and gravitational dynamics. Gravity predicts not only how matter moves, but how space-time separates. Yet even here, gravity remains precise. The equations do not break. They do not produce contradictions. They describe a universe whose large-scale behavior is governed by components that are invisible but measurable through geometry. This reinforces a recurring theme. Gravity is a detector. It senses energy regardless of form. It responds to mass, radiation, pressure, and vacuum energy alike. It does not privilege the visible. It maps the total content of space-time. Dark energy, therefore, does not represent a failure of gravity. It represents an extension of what gravity reveals. It shows that space-time can be shaped by forms of energy that do not behave like matter. Whether dark energy is truly constant or slowly evolving remains an open question. Current measurements constrain variation tightly. No significant change has been observed. Future observations may refine this picture or challenge it. What physics avoids is assumption. Dark energy is not described as a substance unless evidence demands it. It is not given properties beyond what observation supports. It remains a term that summarizes measured behavior. This careful approach matters. Gravity has repeatedly forced physics to revise expectations. Each revision has come from data, not desire. Dark energy continues this pattern. The expansion of space-time is accelerating. Gravity reveals this fact. The cause remains unknown. The effect is measured. Once again, gravity defines the boundary between knowledge and ignorance. It tells us what is happening without telling us why. That restraint is not a weakness. It is the strength of evidence-based science.